All right, welcome to this session. A small change in the schedule. Today we will be covering P&A. I'm stepping in for Sigbjørn that had to go away on a conference. It's quite a packed program today. I have only gotten notice about this yesterday, but I got a few slides from three vendors: Ardyne or Weatherford and Baker Hughes. They supplied information, and we have a little bit also from Archer, quite a lot actually, comprehensive pack from Archer. They were all eager to actually present together with me today, but it was a little bit short notice. What I'm trying to say to you guys is that if you want, I can hook you up with these vendors, and they can show you their technology, how it's done, because they have the latest and greatest in P&A, and there are quite a number of cool features and technology that they have developed. So we can talk about that a little bit later. What I planned for this session, talk about the regulations first. Then we're going to go through an example, and that's an old subsea well that was plugged back in I think it's around 2008. And then we're going to talk about a bit more modern tools and techniques, what it pertains, what is kind of inside it, because the example is just showing you on a big scale what is going on, not kind of what goes on all the stations, how all the different systems on the rig are influenced. Regulations, I'm afraid that the references are not from the very latest standards. The chosen standard was NORSOK D10 from 2013. I am pretty sure from what I remember that the things we are going to talk about today are not any different in the latest edition 2021, if I'm not mistaken, the latest NORSOK. Basically, everything's more or less the same, and one of the reasons why I don't go to the efforts and update myself since I had such a short notice was that regardless, you know that you will be working on the governing documentation for your company when it comes to everything, and those are, as we have shown earlier, more strict or more demanding than the standards. How things work in Norway, you have the government's governing documentation, and then it points very much towards the standards as an example of what is good enough. That's how we do in Norway. And NORSOK, I don't know if you know this, but it is actually worked out by the different oil companies working here, Aker BP, Equinor, others that are active in the Norwegian sector. We didn't say perhaps enough about this slide. You looked at it, so you basically know, and this is known to all of you, I guess, that the barrier, when you place it, should be fully functional in both the horizontal and vertical direction. It should not be one section that is vertically good, and then further up there's another part of the barrier. It should be all across the cross section. Yeah. And the typical barrier program that you'll see, and this is typical for international standards also. You'll see one that is behind me there. Let me see if I can move around a little bit like this. In the bottom, the reservoir plug from flowing. That's a primary barrier very often, and then there's a secondary barrier that would be able to withstand the same pressure regime as the one in blue. And then at the top, there is a requirement to cut down all the casings and remove any infrastructure to approximately 5 meters below the ground. And that's not a barrier that is holding the reservoir as per se. It's more for gas migration and yeah, these things. The barrier type we are using would be cement. That's the one that meets all the requirements. Typically described as a permanent barrier, should have the following characteristics directly cut from the standard: long-term integrity, impermeable, non-shrinking, withstand mechanical loads, chemical resistance, bonding to both steel and formation, and not harmful to the steel, meaning it shouldn't degrade the steel quality in itself, like, for example, acid would. Cement in its liquid form has a pH of above 12 normally, and that's quite okay for standard steel. Not so nice for chrome types, but for mild steel, it's very okay. Here is a description of each barrier and their function. Is basically just the same drawing in the background here. The primary well barrier and its function is described here. Isolate the source of flow, and then the secondary well barrier is a backup to the primary. Cross-flow well barriers, that's typically where there are multiple reservoirs, zones coming in at different depths. And the open hole to surface well barrier is the one that we talked about on the previous slide. That's in green here. And here are the requirements for the different lengths put up in NORSOK D10. Minimum 100-meter long cement plugs. I'm not going to go and read all of these things for you guys, because you're quite capable of doing that yourselves. And going through these classes, you will get to learn the standards quite well, and this may already be well known for you guys. There is also a requirement for verification of the different cement plugs. Some of them need to be tagged with a physical weight where you cannot pressure test them, and others can be pressure tested. There was a project many years back on P&A, looking at the regulations worldwide. Up to the right, we see the American standard back in 2013, 30 meters above and below, 50 meters in NORSOK above and below, and in the UK only 30 meters was required at that point in time. I'm pretty sure that's changed now. Yeah, as said, regulations from your operator would be more into detail. It would be more harder to meet those requirements. Yeah, and so go ahead.
Yes. And if you have a reservoir, imagine 2050 meter,
Mhm.
probably you are going to set a plug from 100 meter, or you are going to put bigger one.
If you if we look at this cartoon, for example, in a quick case, if there's a lot, there we go. If we are thinking that the reservoir below here is very long, um, the barrier is still here. Here is where you can imagine that this is the cap rock, right? Where the reservoir does not, it has not penetrated it. That's why the hydrocarbons are still there. So you may say that it's from the cap rock that really counts. Um, and to complete the answer, let's go back to let me see this slide. Cross-flow well barrier. Here you would be considering if there are issues, and it's not just for uh, the integrity that you're afraid of having hydrocarbons to surface. You're also afraid of your reservoir. Think about having multiple layers, like what you are kind of insinuating in your question, and you're leaving it with just a plug on top. And let's say there are 5 different zones with 5 different flowing permeabilities, flowing properties, and also maybe fluids. So further away, you may ruin other wells because you connect in a well that you have not blocked the crossflow. You connect to reservoirs that then uh, result in, for example, water coming into an oil zone, or an oil zone escaping into a gas zone, or so you also would consider these things, your reservoir, when you do these things. So the crossflow well barrier is not just for the integrity as per se. Yeah. So thank you for the question. Very good. Put me on to something that I didn't think about for this P&A, but it's actually very important, and it's highly regarded when you plan P&A. Yeah. So this is from the course that we used to have with the governing documentation. Yeah, there are different things put up here. Squeeze cementing for perforated intervals, that would typically be to avoid cross flow, as it says here. So that would be the technique in a case where you're afraid of ruining your reservoir in any way, shape, or form. Yeah, possible problems. There are many problems that may occur when we are producing a well over time. Mother Earth is not extremely solid, even though it's hard to drill. It's still a live matter, meaning that it may have slight movements, and that's quite hard on a partly brittle substance like cement. You may see cracks like what you see here. You may have fractured formations. And what sometimes helps us and sometimes works against us would be shales. They tend to swell, and some of them are nice enough to create a bond that are so tight that you cannot on any log see the difference between cement and collapsed shale. and it has the same integrity, more or less. Impossible for us to measure the difference. And shale is also often one of the, call it the cap rocks, keeping the formation in bay. But thinking about this figure is something that I actually put up, talking about well integrity as per se. It's valid for the life cycle of the well when you are producing it, meaning that you will see sources of gas migration here, why you will have pressure in your annuli, and you need to deal with it. In many cases, you'll see pressure in annuli and in wells, not just from temperature rise, but from gas migrating even through cement. That happens even without proper fractures. Cement is just a delay. It's not impermeable, as we are saying. And it says also that non-shrinkable is the requirement. Cement actually shrinks, so sorry. But it's the best material we have, and the closest thing to non-shrinkable and non-permeable. So yeah. All right, that's what I wanted to talk about when it comes to regulations. Here comes a rather long example. In the middle of this example, I'm switching over to another well just to keep everything. It's basically the same setup. Only you'll find it weird that it's another well coming in. It doesn't mean anything. All what this example does is to show step by step what you do in order to make a P&A. And can't remember what the original reason was why the presentation was not good completely, that I had to switch. Okay, so first a little bit about P&A. There are a number of reasons for P&A. Sometimes we do what is called suspension. That is very often a brand new or very good well. You're just waiting to do something with this well, either produce it more, maybe there's some work on the pipelines on surface or the flow line in some way that you just have to plug it. They often do this suspension actually in the Gulf of Mexico when there are hurricanes coming. Hurricanes may sometimes be so bad that they ruin the whole platform, right? And you would like your well to be able to produce and not spill as a function of the destruction that may follow. So you suspend the well by putting in plugs in it. Temporary P&A, that's a little bit different from suspension. Temporary P&A, we'll see an example of it in here. Then you're not really having a complete well. You're either installing a Christmas tree or you're pulling it to either install or remove the tubing, for example. Could be other reasons. But the well is not... you have to do a temporary P&A to establish new barriers, to put it like that. Yeah. Isolation of a depleted target to sidetrack the well to another target. This is called slot recovery. You guys familiar with the term? Yeah, you'll see an example here. That's my main example. And then we have the permanent plugging. And in slot recovery, permanent plugging often exists of the mother bore, the old target. Yeah, example of suspension. You have a completely good well, and you have two physical barriers installed, and they would be typically like a plug like this, and there could be a wellhead plug just sitting here. Two physical plugs in the well. completely isolating it from any flow. Temporary P&A, here's an example where the tubing is missing. There is a base plug here for the cement, and then there is a shallow plug. We often call these big plugs for packers. So that's temporary P&A, and here the Christmas tree has been pulled, and the BOP is about to be run. Yeah, slot recovery. This is the end product, and we'll see the steps all the way coming to this conclusion. This is the motherboard with a typical 7-inch liner, 9/5/8-inch production casing that is cut, 13/8-inch that is cut, and 18/5/8-inch where there is a whipstock installed to sidetrack the new well. Everybody familiar with the whipstock? Yeah, it's a metal wedge, like a triangle, made for tubulars. It's like a gutter, taklinje, that is formed like a triangle, so that in the bottom it completely goes into the casing wall, and in the top it is almost as thin as as a metal sheet, very thin, and the steel quality is harder than the casing, so that when you rotate a mill over this one, you start to eat away the casing, and you create like a window exit. So we'll see an example of an assembly later on, and this is what actually the vendors can show you how this works. It's extremely frequently used, at least in the Norwegian sector, and any type of fixed platforms with a bundle of wells. They have their wells in shafts, the offshore wells that are dry, and in order to get to a new target, you need to do a slot recovery like this, and you try to reuse as many casings as possible. You have to evaluate as a drilling engineer when you do these jobs. Can I exit here instead, or do I need to exit up here? So that's part of your planning. You make a well path going from different places in the well, and maybe different wells too. And some of these whipstocks, they are hollow, meaning that once you're finished with the operation, you can perforate it, and you can get access to this old motherboard. We typically call this whipstock, I know Weatherford, they used to have one called Starburst that is in this category, and we did a lot of that in the Gullfaks field back in the days. It's if you remember the classification, the Tamil classification of multilaterals, that's what, Tamil 3 or 4 or something, where you have hydraulic access to the old well, and you may produce it and commingle with another target. So these are the different types of whipstocks that you'll see. Typically in all multilateral wells, you need a whipstock type of function. One in order to drill a lateral, and the other one would be there to get the completion, if you have any completion type in the lateral, meaning a screen section, a liner section, whatever it would be. You need something to divert that completion into the lateral. Yeah, so on the right here, the originally permanently plugged well, and to the left, the well drilled to the new target. And what follows here is a naming convention. You guys know the naming convention of wells in the Norwegian sector? Yes, yes, you do. Very good. So typically you just add a letter to it, and then you come here. If you add a number, it means that you have lost a section and you're drilling still to the same target. Yeah.
You attach the wheel stop to the drill string directly?
Not to the drill string, to what is called a mill. And this mill is dedicated for eating away the casing. Yeah, we can talk a little bit about whipstock operations, but yeah, that's actually very essential for P&A. Let's talk about the whipstock operation towards the end if there's time. Yeah. Here comes the example from the subsea well. Actually, there are two wells, and we did the P&A of them at the same time. And if you look closely, you can even see the name of the rig. Yeah. So you started out just by running the BOP. The BOP, of course, sitting on the marine riser, landing on the Christmas tree. The full well is intact. This is the other well, and here's where it starts. It shows all the steps. Yeah, I can remember now. The other well was already cemented in part, and the tubing was removed. That's why I put in this well, so that you can see all the steps, also inclusive removing the tubing. Now I remember. I presented this back in 2015 when I was the main lecturer in this. Yeah. Okay. So there is a plug in the liner here, and that's typically something that you would do with intervention. So that was ready in beforehand, and there are many things you can also do actually on well intervention to prepare the wells before the drilling rig comes over, and that's quite normal even on those dry wellhead platforms in the North Sea. You set up a intervention crew on a well, and they would do a number of these steps that we see here. On this rig, that's not physically possible. It's a floater with yeah, so it's not possible, and the light well intervention is not possible either on this field. The wells are too close to each other and too close to the rig, so it wouldn't be feasible. Yeah, so pulling the internal tree cap plug and the internal tree cap. This is an Aker subsea system. I'm not sure what they are called anymore, but back in the day it was called Aker. Next step is to install Dwigs. Dwigs is just a guide to be able to run Y-line in the well. Any marine riser is a little bit deviated, and anything will always go to one side, and it's very hard to enter in the well and be able to retrieve the tubing hanger plug with Y-line unless you have this guide installed. That was experience, and then Y-line is rigged up with no pressure control, as you can see, because it's directly in the marine riser. You run straight down, you pull the tubing hanger plug, and then you punch the tubing for the purpose of being able to circulate down the tubing and up the A annulus from the bottom. You may not see it, but it's down here, and it's a slightly red thing like the perforations here, showing that you're punching. We call it not. We don't call it perforating. We call it punching. The reason being that you don't want to have explosives that are so strong that they may do something with the integrity of the casing outside.
Could you explain again?
What we do here is to run a puncher, tubing puncher. It's a call it a puny perforation gun. And what it does, it just makes a hole in the tubing at this point. Here, it makes a hole in it. Then they pull this guide, and the simple reason for that is to be able to hook up the tubing hanger running tool on a landing string, and then you can pump down here and out the hole that you made, and you circulate out. It has actually two main purposes that I can think about from the top of my head. The first being that basically you want to get rid of any gas that has migrated into there. You may wonder why and how, but it does. There's always gas everywhere after. Just give it time, and there will be. Um, Another thing that is very important is actually to get rid of debris, dirt. It is if you have enough debris, it's more or less impossible to pull any pipe free. If you have ever put your rubber boots when you go out in the nature into marsh, into myr, it gets like right, and then when you try to get out, your feet go out of the rubber boot because it's there sucked, stuck. And that's what happens here, and to casing in open holes and so on. And that's I would say that's the prime, call it evil or problem. I wouldn't say it's the prime problem as per se, but it's the root cause to so many things with P&A. Cost driving. Imagine you're trying to pull out pipes from an open hole, and they are like stuck to the formation. Very often what you can be able to release, at least back in the day before the modern tools came about, we were able to pull and jar free, hammering with all what we could, 5 meter lengths of casing, and that casing was more or less just set. That's an experience from one of the fields that I worked on. It's incredible how much the formation actually, call it it's like a capillary effect, I guess. That kind of clings or glues or sticks to the pipe, and that may happen in the cased hole too if you didn't wash it properly when you install the completion. That's gonna be one of the things, and we have seen it, that it's extreme weights to overpull beyond the normal. And what is the normal? Here is the thing we call the PBR, polish bore receptacle. It's pinned with a metal ring, and there's a certain force that it needs in order to overcome it, and it splits up to a stinger and a PBR, female and male part, and that's installed not to take thermal forces, as many may think. Very few wells actually require that. Extreme HPHT maybe. It's more to be able to do recompletion. In case a tubing leaks, you pull the old tubing at that point and you establish a new packer above. So we have circulated the well clean. We have good fluid there, no hydrocarbons, nothing like that. Then we are ready to pull the whole completion out. We pull on the PBR, stinger, and female part. We install a bore protector. That is for the reason to protect the seals that are inside the Christmas tree, where the tubing hanger goes. and also the plugs, of course. Very important to log the cement if you don't have a proper log from before. Also, in modern times, we look for other means of integrity, like a shale collapse would help, where that is allowed. Again, that was yeah.
Would you also want to log for like casing wear
Yes.
in the casing?
Yes, definitely. So you log both the casing and the cement. Thank you for asking, because I forgot to say it. Of course, you would check for casing wear at the same time. Um, yeah, one of the things that also would be important actually is ovality. If the casing is oval, it will reduce its strength, especially collapse. Not burst, but collapse. Um, I've seen when you set so imagine that you're going to set a plug in it or run something. It doesn't have the proper ID anymore, and also it won't give you the same integrity that you were meaning and hoping for, aiming for.
Happen? How does it become oval?
Um, Actually, there is a certain ovality on all pipes as they are produced. That's one thing. Another is over time, if there's in situ stress in the formation, you will have that. So yeah, it could increase ovality in that case. It's just it's not very often, and a lot of people actually think about it. But I've seen cases where. Let me remember. Yeah, we were supposed to run a tieback, and we set the yeah. You know what a tieback is? Um, it's actually, this is the liner hanger, right? It stings into the PBR. It has a piece of pipe and it has a packer. That actually looks like a tieback. If say that you cement this liner and you find out that okay, it's still leaking. It's still leaking here. I didn't get the integrity that I hoped for. Okay, then you run a tieback. Always when you run liners, you have a tieback in backup in case there is a problem with the cement job and you want to do a top squeeze and yeah, different things. You want to have a tieback ready at hand. Um, we were running a tieback over an area with very high casing wear, and the casing was actually so oval that when we tried to set it, it has absolutely no integrity, nothing. So we had to pull it out, a half set packer like this, and we actually managed. So that was yeah. Okay, that's another story. Good question again. Thank you, guys. Cementing the primary barrier plug. You guys know about the balanced cement plugs and how they are done? No. You see an example here. I will not go into that too much detail, but it's the primary method of establishing cement plugs in wells. Typically what you do, you have a long stinger. You see that it's a very thin one here. Typically it's 278 or in some cases 3.5. Better with the smaller one because you pump a plug until it's balanced on the inside and outside. And as you start pulling out, the cement on the inside is replacing the steel that you pull out of the plug. This method is by far the one that gives you the least contamination. As you see when you're staying right here and you're pumping cement, first the spacer to clean both the drill pipe on the outside and the casing on the inside. Then you place the cement. Then you have a good length of clean cement here, right? It's kind of simulating the cement job as it would be on the outside of the casing. The other method is called pump and pull. And that is what you do when you have like a tube of caviar or cheese, and you squeeze and you pull along your slide of bread. Yeah, that's pump and pull. And that means that you have an interface between the the mud and the cement all along at the end of the pipe, right? So the chance for contamination is a little bit higher, I'd say. Yeah. That's at least the old school learning. There could be techniques and tools now that are allowing it to be better.
Question.
Yeah, go ahead, please.
Okay, before starting with installing the plant, you have not checked the integrity of the cement behind.
Yes, we did. We did that. We logged the cement and the steel.
Cement?
Yes, the cement. Let me see. Here, log casing and cement.
Yeah, but you just log. You have not ensured it's integrity. You have integrity.
You see it. You see it. If the integrity is not good enough, then you have to do something like milling and creating a cross section. In this case and in this the integrity was good. So you can just start cementing, and you are creating a good cross section here. The integrity in this area was good with regards to the cement and the steel of the casing. Okay. If it wasn't, we would have to cut and mill away all of this in a section. It's called section milling. I just added that to to the slide as just before you guys came here, so we'll see not a very good drawing of it, but you will get the understanding hopefully from this session. Yeah, and thank you again for a good question. Now we switch back to that other well. Status is the same. Plug and a tiny cement plug. Requirements, according to Equinor at least, is that you have to cement all over this transition. You have to cement all of it. It's this is not. This is just a start, to put it like that. Half the job. Otherwise, it's an identical status. You see the tubing is gone. You're installing the 958 packer. The packer is there, and you pull the BOP. That's the next step. Then you pull the Christmas tree, and the Christmas tree is worked over, and you can use it on another well. Yeah, and then you run the BOP on top of the wellhead. Now you cut and pull the 958-inch casing. You see it's cut here at a certain depth and pulled out. You install a 13-3/8-inch packer in the casing just above the cut. And that packer will be, it's a permanent plug actually, will be the base for the next cement plug. Then you cut in the open hole. That's the difficult part. That's where the casing is properly stuck. But you will be able to get rid of it. There are different ways and approaches that you do. You cut down to this depth maybe and pull out. And it works in the same way when you cut away the casing here as you did for the tubing. You have to punch hole in the casing, and the old mud on the outside has to be circulated out. And you have to be careful, because if it's an old water-based mud, unless there is H2S scavenger in it, you may actually have H2S forming there, even if it's not naturally occurring, because bacteria exist that live in this environment and they produce H2S. It's part of their, call it gastro process, and it's the part that is what they deposit that makes the H2S. So they're the more the H2S, the happier they have been, and it has surprised a lot of engineers over time. So make sure if you do and plan a P&A and there's a water-based mud in the annulus, make sure that if you don't know if they added the H2S scavenger before, add H2S scavenger when you circulate the returns and take precautions, have masks and alarms and sensors everywhere. So yeah, important. So basically you cut up here, you pull the upper part of the casing, that one would be free for sure. Very often you log that casing too, simply to know, is it stuck in the open hole? Is it stuck inside the casing? I'm gonna round off so you get your recess now, but I'm just gonna show you why would it be stuck in the casing. See here, see if the shale is collapsing and the barite is precipitating, then it becomes like a sand plug inside the casing. It's very, very common, very common. And you can just forget about trying to cut it at the shoe here and pull it free. With more than 10 meters of a barite plug like this, it's going to take tremendous force to get it loose. So typically what you would do, you would cut above here, and then you would start to cut at your other depth, and you would try, am I able to get it free? You get more overpull available. Getting rid of this part. Yeah.
Right, with the precipitation, does that mean that it's better that has
Absolutely, absolutely. It's the barite that was in the mud once upon a time. Now it's water more or less on top here, or if it's an oil-based mud, it's pure base oil on top, and then all the good stuff is sitting down here. Yeah. All right. Let's call that session number 1. I'm interested to see how many slides we covered, basically. Luckily, we are a little bit longer than this. Yeah, we're here somewhere. Yeah, and that's 37. Oh, you have to speed up. All right, try to be back on time. We have a lot to cover. Sorry for that.